Hello everybody, my name is Peter Klapper from the School of Biosciences at the University of Kent in Canterbury, and in this video clip I want to discuss with you a different kind of growth kinetics, something that is very frequent when we, for example, look at the growth of a population. When we are talking about growth, we very often think about, for example, the growth of a population, be it bacteria or rabbits or something like that. Now, how would we write and depict this? Now, previously, we looked at first-order reaction kinetics, where we had a reaction, a reactant A, and this is converted into a compound B. And we said we can depict this if this is a first-order reaction. We have here the time axis, and we look at the concentrations of A and B. And what we found that is, if we look at A, it disappears, something like that. And at the same time, when we look at B, it grows like that. And if it is a 1-to-1 ratio, that means 1 molecule of A gives 1 molecule of B, then our limitation that we are looking at here, our limitation would be this A initial here. So it would be A initial. And we would never get any more product. So we would never get any more B than we had A initial. And we developed the equations for that. So we said, for example, A initial, A at a time point t equals A initial times e to the minus k, and k is the rate constant here, k times t. And we also said B at a given time point equals A initial times 1 minus e to the power of minus k times t. So that's sort of revision. But now, what happens if we have growth of some kind, say a bacterial culture? What we see is that this bacterium doubles and then doubles and then doubles and then doubles. So it doesn't have something that is limiting in a way. So we would not be able to write it as something like that, where this is our bacterium. That would be wrong. So we could, however, depict it as something B is produced and produced and produced. And we would obviously write this in a graph. There's no A there, so we would look at it at time. We start off with something very small, and then it goes up and up and up. And there's no limitation, because there's no A limiting factor. And that is a true growth curve here. Growth curve. So how can we write this as a kind of an equation? Now what we can say is, okay, we have the scenario where B is produced, and therefore we can write dB over dt, our differential equation, that is the general rate law, equals, and now we have a production. We don't have a consumption as we had before, but now we have a production. And this production depends strictly on B. So it would be consumption plus K, that's our rate constant, K times B, and if it is a first order reaction, it would be to the power of 1. So what we can do is, we can really say B at the time point t equals our starting concentration, B initial, times E to the power of, and now here it comes. It is not a consumption, it is a production, so it would be plus K times T. And you hopefully see here this plus. That brings it to what is called a logarithmic logarithmic growth. So this is an exponential growth. Exponential growth. And I hope you see the difference between the limitation when we produce b from a or when we have exponential growth from a. Let me again stress this fact, because I know that a lot of people mix these things up. If we have a is converted into b, then we have something like that. That's time here. And for b, we would see something like that. So that's b, and this one here is a. If we have logarithmic growth, what we would find is time again. What we would find is something like that. So that is our b. And I hope you see the difference between these two things. Here b is produced from a, but here b just simply grows and grows and grows. Thank you very much for watching, and I hope this makes sense.